Okay, so this is a review on our exponential and logarithmic properties and equations. And so we're going to start out by looking at how to evaluate logs without a calculator. So there's two things that are really important to recognize. One is that when I read this out loud, I read this as a log with base 7 of 1 over 49. So that's how I'm going to read that. And whenever I see a log, I always think to myself of the log as asking me a question. So this is saying, if we raise 7 to what power would we get 1 over 49? So you can even write that question out. 7 raised to what power would give me that 1 over 49? So right now, I'm going to go ahead and ignore this 1 for a second and think to myself, what if I raised 7 to what power to get 49? And we know that 7 to the second power will give us 49. But then we have to figure out, how do we get that 49 not in the numerator but down here as 1 over 49? And that's the reciprocal. And a negative power is what will do that. So 7 to what power will give me 1 over 49, that will be the negative second power. The 2 will square the 7, and the negative will move it into the denominator. Okay, when I look at this one, this is saying 6 raised to what power gives me 6 to the negative second power. So there's a couple ways I could do this. One favorite way that I could do this is I can use the power property to pull that negative 2 as a coefficient here. And that makes it a little easier to digest, a little smaller pieces. So we have 6 raised to what power gives us 6. And that is just 1. 6 to the first power gives us 6. So we just have negative 2 times 1, which happens to also be negative 2. That's why students sometimes talk about these things as canceling each other out to leave the negative 2. It's because if we pull that negative 2 forward, we just say 6 to what power gives us 6, and that's 1. So it, in a way, makes a 1, just like when we cancel things in the numerator and denominator of fractions. Okay, when I see ln, I have to know what base that log is, and that's a log with base e. Anytime I see ln, I can replace it with a log base e. So that can help me think about what it's asking. And so it's asking me e to what power gives me e, and that's just the first power. Anything to the first power gives you itself. And then this last one can be kind of tricky because whenever we're looking at it, it can be hard to envision what 0.25 is. And I find it helpful to do two things. One is to pull that x in front. So then I have of 0.25. But instead of putting a 0.25 here, I find it helpful to put it as a fraction. So we know 0.25 is the same thing as 1/4. And for me, that's helpful because now this part of the problem looks kind of like this, right? We know 2 squared would give us 4. So to get 1 over 4, that would be the negative second power. So 2 to what power gives us 1/4? That's the negative second power. So then x times negative 2 gives us negative 2x. So now we're going to look at 2 solving examples. This is an exponential equation that we're going to look at first. And when I'm solving this, the first thing I want to do is to get this piece of the puzzle by itself. Because I can't undo that power without getting it isolated first. So I'm going to start by adding 3 to both sides. So I now have this. And then we know that exponentials and logarithms are inverse operations of each other. So I can apply a log with a base 6 to each side as long as I do it to both sides completely. And so if I apply that to the left side, we have log base 6 of what we had before, 6 to the negative 0.2x. And then to the right side, we have log base 6 of 10. And as long as we do it to the both sides, we are good to go. We're keeping the equality of that equation. Then, when I look at this, I recognize that just like we were doing before, 6 to what power gives us 6 to this is going to undo each other, or we can think about moving this to the front, and then 6 to what power gives us 6, and that's 1 times negative 0.2x. So however you want to think about it. But just like before, that helps us get that exponential out of the power. And so I have this, and then all I'm going to do is make sure that I divide both sides by negative 0.2. And we get our answer, and we can just find out what that is as a decimal. And that gives me negative 6 let's just round to the hundredth place. You'll always get instructions about how to round, but we get negative 6.43. So that last problem was a exponential equation that we solved. This problem is a logarithmic equation that we're going to solve. And just like before, we cannot solve this until we have just a single log isolated by itself. But right now we have two separate logs. So I am going to use the product property, because these two logs have the same base and they're being added. So that means I can use the power property to multiply their arguments and condense that into one log. So I have to make sure that I'm multiplying it using my distributive property. So now I get this equation. And I really need to undo this log. And like we said before, logarithms undo exponentials, exponentials undo logs. So one way to think about it is by saying we are going to rewrite this where both sides are a power on 6. And I chose 6 because 6 is what will undo this log base 6. And that will help me rewrite this equation and pull that argument out of a log. And then 6 squared we know is 36. So now we have a quadratic equation, which we know we can solve by factoring, completing the square, or using the quadratic formula. And let's see, looks like it will factor nicely. And so let's see if I can make a little more room there. So I'll get x plus 18 equals 0, x minus 2 equals 0. So I get x equals negative 18 and x equals 2. But there's something we have to be careful about. When we have logarithmic equations, sometimes we're going to get what's called extraneous solutions, which means we did everything right in the solving process, but we might get an answer that when plugged back in won't actually work. We know that the argument of a log, it has to be greater than 0. Logs are only defined for values where the argument is positive. So I have to take both of my solutions and double check that when plugged in here or here, that they don't create a negative argument. And when I plug in 2, I get a positive argument. When I plug in 2 here, I get a positive argument. But when I plug in negative 18, that makes this argument negative, which we know is not really defined. So that makes that solution extraneous. It doesn't actually work. It's a solution that we got while solving correctly using correct mathematical work, but it's an extraneous solution that when we go back and check, it actually creates an undefined equation right here. So we can't continue. So we do have one solution. X equals 2 does work, but we have to cross out negative 18. It does not work. Okay, so now let's take a look at some problems in the real world where we might see exponential growth or decay and be able to use it. And we have two financial examples here that I want to look at. And so there's two different equations you might use in these financial situations. One is the compound interest formula. That's when you're going to use that one when you have interest that is compounding a discrete number of times per year. For example, if it said it's compounding once per year or twice per year, or it's compounding monthly, so it's compounding 12 times per year, or even if it's compounding daily, so 365 times per year. Those are all discrete a discrete number of times that you are compounding that interest. Whereas here we have the compound continuously. And the thing that will help you notice to use this formula is when it says compounding continuously. That means that at every moment it is compounding your interest. So it's as soon as it finishes calculating and compounding your interest, it immediately begins doing it again. So it's faster than even seconds are happening. And so this is our formula for compounding continuously. So in this first example, it says you deposit $400 into a savings account that pays 5% annual interest, and it says that the account compounds quarterly. So that's a discrete number of times per year. So when I'm going to substitute this in, my P is going to be the principal. That's how much you're starting with. Your R is the rate that you're paying, but it's always written as a decimal, not a percentage. So the account is paying 5% interest, which I'm going to write as 0.05. And then the N is how many times it's compounding per year. So in a year, if it's compounding every quarter, that means it's compounding 4 times in that year. And then the T is always time. How much time are we going to give it? So in this example, that is 10 years. So I'm just going to substitute right in. So 400 times 1 plus 0.05 divided by 4, all to the 4 times 10. And I have to be careful as I enter that into my calculator and make sure that I'm following order of operations. And when I do this, I find out that in 10 years, I will have $657.45. Excuse me. We'll round to the nearest cent. And that's all there is to it. Now, in this second example, it tells us that we have a set amount of money that we're depositing into an account that compounds continuously. And so whenever it gives us that continuously word, we know we're talking about continuously compounding interest, which is this A equals PE to the RT. So again, P is my principal, which is how much I start with, so that's the $300. E we know to be a number, right? That's Euler's number, that's 2.718, ... And then the rate is 5%, so that will be 0.05 again. And then the time this time is 6 years. So the rate was 0.05 and the time was 6 years. So again, be careful as you're entering that into your calculators. And when I do that, I find out that I will have $404.96 rounded to the nearest cent. Okay, we're going to look at one more example. This is an example of exponential growth or decay. And so we have two formulas. They're very similar. One is for exponential growth and one is for exponential decay. Now, these are just starting points for building an equation or a model that helps you model what is happening in the scenario. So the A is always going to be the initial amount. Now, it's not always going to be money. It could be a population. It could be, how many molecules we have. It could be anything. The R is again going to be the rate of growth or the rate of decay. Also, just like before, it's got to be written as a decimal. And then the T is going to always be time, just like before. So the only difference here is that growth is going to be 1 plus that rate, and decay is going to be 1 minus that rate. And so if we have a number greater than 1 here, in our equation, sorry about that, Belle. If we have a number greater than 1 here in our equation, we can see that it's growth. If we have a decay problem, we see that we're going to end up with a number less than 1 as the base there. So in this example, we know that the equipment costs $95,000. That's the start of the problem. That is our A value. And it's depreciating at 14%, which is going to be 0.14, written as a decimal. And because it's depreciating, that's what tells me we're going to use this decay formula. And then we're trying to find the value after 5 years. So I'm going to substitute into that formula. 95,000 is my initial value. I'm decaying, so I'm taking that 14% or that 0.14 away from the 1. And then we're looking at 5 years of time. So when I look at this equation, my equation ends up being 95,000 times 0.86 to the fifth. And so what that's saying is that each year we have 86% of the value that we had the previous year. That's why we take the decay rate away from the 1. So we can type that into our calculators to find out that it will be worth $44,690.57. Now, if we had had a growth rate, if it had said that, because some things gain value each year. So let's say that, if I were to think about my house, a lot of times your house gains value over the years. So let's say it gains value at 2%. I would be plugging in, here would be my A value, which would be how much my house is currently worth. Then my growth rate, I'm growing at 2%, so that'd be 0.02 over time. And so that would give me a base of 1.02, which is more than 1. That's how I know it's growth. And what that's saying is that it's worth 100% of what it was worth before, plus an additional 2%. So each year you're gaining 2% on what you had before. That's why we're adding it to the 1. Okay, good luck. Study hard.